Hello everybody, welcome to Blue Marble Science. One of Nathan Oakley's guys has discovered how an atmospheric pressure gradient can work without gravity, or maybe not. One of the guys has come up with an extremely well thought out hypothesis to explain our atmospheric pressure gradient. So, let's light this dumpster fire and have a little fun. One of Nathan's lap dogs, a guy named Chris, became aware that our atmospheric pressure gradient is a real problem for the flat Earth. Now that makes perfect sense. Everything else is a problem, so why would pressure gradient be any different? So after an extensive 2-day period of self-tutelage, which apparently consisted of reading wiki articles and doing Google and YouTube searches, Chris has cracked the code despite no apparent formal training in the field of physics. With backup from some sophisticated research work being done by another YouTuber by the name of Good Times for All, Chris has discovered that gas pressure is related to the temperature of the gas. Wow. Astounding. And according to Chris, our atmospheric pressure gradient is caused by warm air rising. Did I read that right? Yeah, that's what he said. Warning. The following video is not suitable for small children. They already know better, and watching this codswallop will only confuse them. Be sure to move your monitor out of punching range, and always wear your personal protective equipment, including safety glasses and face palm protecting oven mitts. Okay, Chris, go for it.
I was trying to get my thoughts together. So the last couple of days, I've been doing research on gas pressure gradient, based on Good Times for All's video that he did. In fact, I have it up here because I want to give him sort of credit for my trek down this research. And so, obviously, you've been plugging this video and talking about it. And I mean, this demonstration alone debunks, the baller claim that you can't have a gas pressure gradient in a container by itself. So pretty much you can point him to this video and sort of go about your day. But I wanted to do more research and see what there was to this, because I really didn't know why he did what he did or why it would cause a change in the gas pressure itself. So after I watched this video, I noticed he was taking this sort of like down here, it's like I don't know, not a blow dryer, but like one of those, a heater or something, and he was heating up the outside of the containerized pressurized tank here. And I thought, okay, well, so obviously if he's changing the temperature, well, that must have something to do with the gas pressure inside.
Easy, Big Blue. That's right. Chris has single-handedly discovered the universal gas law. You know, the one that says P1 V1 over T1 equals P2 V2 over T2. Oh dear, I don't think this is going to go well.
Hello everybody out there in YouTube land. Good Times for All, is Zachary Zabala here if you prefer. In this video we're going to explain what we're doing here, and this is just a very rough start, folks. What we have is a bucket of ice water, okay? This is a little too warm to be touching right now. This is one of these turned over. It has one of these on the bottom of it upside down in the ice. It is held up. Oh, it's held open right now. So, and that hose is coming out right here, and it runs up to this pressure reading gauge right here, which is, as you can see, is right at about 3. And this one is right at about, it's under 2.5. Almost to 2. What I've done is I've taken this heating gun up to 800 degrees, and then we have the bucket of ice water at the bottom, and I'm changing the temperature, hopefully, at both ends. So we have the cold at the bottom and the heat at the top. And what we're finding is that we're getting a little bit more pressure on the bottom. Just a hair, possibly. What we really need is another one of these gauges right here. Now, in fact, these gauges may not be 100% accurate. They're old. Some of them are sticky. So this is really just a rough start, folks. This may not actually be doing what it looks like it appears to be doing. So that one's at about 2. We need this one. It appears it's at about 3. So we have, we need better equipment. So I'm really just throwing this out here so other people can maybe try it or give me some ideas to make it better.
Yes, I have a great idea. Stop. Just stop that. I don't want to get too carried away here because I actually think it's great that Good Times has taken the initiative to try and actually do an experiment. Most of the flat earth crowd are just like Oakley. They sit on their flat asses and run their mouths a lot, but you rarely catch them actually doing anything. But Good Times is discovering what I already know from a lot of years of doing research work, and that is doing the experiment really is simple. Figuring out a reliable method to do it, coming up with the appropriate test equipment, defining a test plan, so forth and so on. That can all be pretty tricky if you want to end up with believable results. So here's a couple of problems I see. If you're trying to simulate Earth's atmosphere, you got the heat on the wrong end. The top of the LP cylinder needs to be cold and the bottom needs to be heated. That's the way the Earth works. And anytime you're using multiple measurement devices that have to be compared to one another, you've got to have some way of calibrating them. I could go on and on. Let's just leave it there.
When describing conditions in the atmosphere, and may also be referred to as atmospheric pressure. So yesterday, somebody was trying to get a got-you on you by saying, oh, well, we're talking about atmospheric pressure. Well, it's all the same thing, right? And this article says as much. Okay, so I want to sort of skip down a little bit. Here it says, at higher altitudes, air pressure decreases because there are fewer air molecules pressing down from above compared with the air pressure at sea level. Okay, so that in and of itself is your gradient, right? So this article doesn't say the word gradient in it, but it's a logical deduction that they're talking about a gradient based on temperature. So let's dig a little bit further into it and see why we might have an air pressure or atmospheric gradient as we do in our atmosphere. So here it says, talking about warm temperatures. Okay, warm air causes air pressure to rise, right? So where is it warmest at? It's warmest at the surface, right? Warm air molecules collide, they exert force on each other. When gas molecules are heated, the molecules move more quickly, and the increased velocity causes more collisions. As a result, more force is exerted on each molecule, and air pressure increases. Okay. Temperature affects air pressure at different altitudes due to a disparity in air density. They're basically telling us that temperature is changing the density of the air molecules. And as we all, well, I can't say that, but what I will say is my opinion and my research is that what we know as gravity is all due to density, relative density, and buoyancy. And this basically is telling you as much for its impact on air molecules. Okay, this last is a little bit confusing, so I'm going to skip that. Okay, cool temperatures. Cold temperatures cause air pressure to drop. So what happens when you go from the hot surface and you rise in altitude, and it gets colder and colder and colder the higher you go, the air pressure is going, it's naturally going to drop because of the colder temperature. So basically the theory is as the hot air on the surface as the air heats up on the surface, it causes more collisions. It's a higher gas pressure. It then rises, right? Hot air rises. We all know that. And as it rises into the colder temperature, it moves more slowly, and the pressure drops. the air is your gas pressure gradient.
Okay, Chris, I got a question. Why is it monkey turds like Nathan religiously harp on the scientific method and pitch literal shit fits when one of us doesn't dot every I and cross every T, yet when it's your turn, all we get is this? Okay, I'll do it for you. Your observation is the atmosphere has a pressure gradient. Your hypothesis is the temperature causes it. The independent variable is the temperature of the air, and the dependent variable is the air pressure versus altitude. So, let's test your hypothesis. Now, since you haven't done an experiment and you don't have any data, let's use some other information. Let's assume the surface temperature is 100 degrees Fahrenheit and the temperature of the atmosphere at 30,000 feet is negative 60 degrees Fahrenheit. Using the universal gas law, and now remember, volume is constant. Volume of the atmosphere doesn't change. So we can ignore that term, and it becomes simply P1 over T1 equals P2 over T2. 14.7 psi at sea level and 560 degrees Kelvin is equal to 10.5 psi at 400 degrees Kelvin. Whoops. 10.5 psi is an atmospheric pressure that you would expect to see around 10,000 feet, not 30,000 feet. Here's an online calculator. 9724.3 to be exact. Now let's try the barometric formula. The barometric formula says pressure equals whatever pressure unit you're using. In this case, we'll use 14.7 psi times E raised to the negative GMA divided by RT, where G is the gravitational acceleration, M is the molar mass of air, A is the altitude, R is the universal gas constant, and T is standard temperature, 273 degrees Kelvin. Plug all those numbers into that formula, and the barometric formula predicts the pressure at 30,000 feet will be 4.681 psi. Here's some balloon footage from a YouTuber by the name of Dwayne Kellum. The link to the video is down at the bottom. Dwayne does some really nice balloon work, and he has his balloon outfitted with instrumentation giving us the actual air pressure. And as you can see, at 30,000 feet, the balloon's measured pressure, when converted to PSI, matches our prediction within 2.2%. I would say the barometric formula describing atmospheric pressure is a decreasing exponential function dependent on gravitational acceleration is totally correct. You know, sometimes it takes a little more than a 2-day Google search to work these things out. Occasionally that math you flat earthers find so objectionable comes in pretty handy, and a little technical education never hurts either. Sorry, Chris. It isn't hot air rising. It's gravity. Hey, thanks for watching. Don't forget to hit those like and subscribe buttons, and we'll see you guys on the next one.